Alrighty, so we're going to move on to section 8.1. So this is the start of new material. This is going to be the last, so this is going to be the only section, part of section 8 that we do. We're going to move on to polar coordinates after this. So the idea behind this section is, this section is called arc length. And so what we've been doing now is we've been computing areas. So up until now, we've been computing areas underneath curves. That's one way you can think of the integral. But now we're going to turn to the question. So now we have the new question. How do I find the length of a curve? And this is so this is actually an important question. So we're going back one dimension. So areas are two-dimensional things, and we're going to go back and talk about how to find this one-dimensional length. And then next semester, if you're going on to Calc 3, you'll go to 3 dimensions and talk about volume. So the idea behind this is, if I have a curve, so let me draw, just a curve that looks like that, and I want to find the length of this curve. One thing I can do is I can think about, first thing I can do is I can, take the endpoints here, connect them, and that'll give me, some sort of approximation. So if I just find the length of this line, that'll be an approximation to the actual length of the curve. And we can keep doing that, so if I have the same curve, instead of doing, the two endpoints here, I can bisect it, so cut it in two, find the length of this line, find the length of this line. That's going to give me a better approximation. And now I have 2 lines here. And I can keep going. So you'll see that, the more lines that I bisect this, or that I cut this into, the better the approximation is going to be. And you can kind of guess where this is going to go. We're going to start involving some calculus. So let's call this, let's label these points. So let's call any pair of points. So sorry, this is a notation thing. So let's call the line, I'll write a little slower, connecting the points, P1 or PI. So we'll do PI minus 1 and PI. We'll call this line just PI minus 1 PI. So that just means, it's talking about, it could be talking about this line right here that I've just put in black on the figure there. So it's just talking about, any line segment there, the length of that line segment, or we're just calling that line segment PI minus 1 PI. And we'll call the length of PI minus 1 PI, we're going to write it like this. So the length is going to be PI minus 1 PI, and we're going to stick absolute value signs around it. There's a reason for this, and you'll understand a little more when you get into higher dimensional spaces. So then we can call, the approximation will be, so we're going to add up all these line lengths. So it's going to be the sum from I equals 1 to n. So if I break it up into n different lines, I just add up all these line segments, all the lengths of those line segments. And then we can get the true length by, if we keep dividing this thing and dividing this thing, that's taking a limit. We're going to take the limit as n approaches infinity of this sum. So this stuff is, so right now I'm kind of explaining where this formula for arc length is going to come from. This is a little more, theoretical than, what you guys are used to with just seeing examples. It's fine. Let your eyes glaze over. It'll be over in a minute. Okay, so let's figure out what the lengths of these lines are. So we know from, basic geometry that the length of a line is going to be the square root, and it has to be symmetric, so it's going to be x sub I minus 1 minus x sub I squared plus y sub I minus 1 minus y sub I squared. So I'm just writing down the length of a line. So this thing here, this y sub I minus 1, let me clean it up a little bit because it looks like y sub I, y. This thing here, so because, I'm thinking about this in terms of a function, I'm going to scroll up here. Let's call whatever this function is, f of x. So I can think of this as, f of x sub I minus 1 minus f of x sub I. So that I'm just evaluating, the function at those x values to get the y values. Now we're going to go back and we're going to use something that we talked about, last semester. You should have talked about last semester. So by the mean value theorem, so remember the mean value theorem says that, there is some, so on any interval, say, it has to be a closed interval, x sub I minus 1 to x sub I, we have the following. There is some point, x sub I star, such that the derivative is equal to the average value, to the slope of the secant line. So this is going to be f of x sub I minus 1 minus, sorry, that should be the other way around. F of x sub I minus f of x sub I minus 1 all over x sub I minus x sub I minus 1. And now we can solve this. So we can solve this equation for f of x sub I minus f of x sub I minus 1, and we're going to replace it up there. So what this ends up being then is, yeah. So what I'm going to end up finding here is that f of x sub I minus f of x sub I minus 1 is going to be equal to f prime of, some point on that interval times delta x here. And that delta x is x sub I minus x sub I minus 1. Okay, and how does this help me? So now if I take this and put it back into the length of this line, p sub I minus 1, this is going to be the square root of, so this first term here, that first term that I've just highlighted is just delta x squared. Again, you can pause the video if I'm moving too quickly. And then we're also going to add, and we're going to replace, this f of x sub I minus f of x. So we're going to replace, so we're going to replace this term with what I've just solved for here. And don't worry about the minus sign. I'm squaring that difference up there so I can, take a minus sign out and switch the order. It's fine. But what this is going to be now is this is going to be f prime of x sub I star squared times delta x squared. The idea is now I can pull out the delta x squared. I'm going to get 1 plus f prime of x sub I star squared times delta x. And that's going to be the length of any one of these lines. So then I'm going to take this and I'm going to plug it back into the formula for length, and this is the limit as n approaches infinity. The sum I equals 1 to n, square root of 1 plus f prime of x sub I star squared delta x. And as I let n go to infinity, you can see that this is the formula for a Riemann sum. And the formula is for the square root of 1 plus, something here. And when I take that limit, I'm going to get that the length then is the integral from, over the interval that I'm working on, the entire interval, square root of 1 plus f prime of x squared dx. And this is going to be my arc length formula. So what I did there, and again, it's kind of a derivation. It's not like anything rigorous. But what I've done is, I wrote down an expression for an approximation for the length of this curve. And then I said, okay, the true length is given by this limit. And then I said, okay, how can I, turn this into something that I can actually evaluate the limit on? The way I did that is to write things in terms of, this, using the mean value theorem to bring in the derivative of the function. And from that, I was able to get a Riemann sum that I turn into an integral when I take the limit. But anyway, so if all that went over your head, you weren't paying attention looking at your phone while I was talking. This is kind of the crux of the chapter. Let me write it a little neater. So this is how you find arc lengths of curves, in the two-dimensional space we're working in right now in the plane. So the length is going to be the integral from a to b square root of 1 plus f prime of x squared dx. And I'm going to write this another way. So the way the book gives it is length is equal to the integral from a to b square root of 1 plus dy dx squared dx. And so, of course, you need, on this, when I was doing this, I was also assuming that, the function is continuous, things are nice. So I'm going to stop the video here. This is probably getting around to the 10-minute mark. That took a minute. Again, this is, the main thing to take away from this, this length, this formula for length, where I'm going to do some examples where I go through and calculate these. But you can kind of see what's going to happen here. It's going to come down to evaluating the integral of this thing, square root of 1 plus dy dx squared. And so in order to be able to do that, we're going to have to, kind of be handed things that are easy to integrate in that sense. And so, so I'm going to stop here, and we'll do an example next time.